connection so that no single point is able to learn both Alice and Bob. Yes, if R1 is bad, he knows Alice is using Tor, but he doesn't know what she's doing. And if R3 is bad, he knows somebody's talking to Bob, but he doesn't know who. And if they're both bad and they're colluding together, we're screwed. But at least we're doing better than one point of failure. So that means that the security that Tor gives you comes from how big the network is, how diverse and dispersed the servers are. If we can get 1,500 different servers all around the world in different places, then as the network grows, the number of attackers who are able to be in both of these places shrinks. So as we grow larger and larger, there are not as many attackers who are able to be in the right places to beat Tor. That's the goal. What sort of background do people have on crypto? If I say ephemeral Diffie-Hellman, stuff like that, will you stare at me blankly? Looks like, okay, sounds good. So I'll give you the basic overview of how the crypto works in terms of what security properties we get. So the basic idea, Alice is going to pick her path through the network, and I'll tell you later how she does that. And she's going to connect to the first guy and establish a session key. So there are two properties that we're looking for here. One of them is nobody who watches the traffic going over this link can read it once they've established the session key. Another property is Alice convinces herself that she's talking to the right person. She's talking to R1. That's done with public key crypto. And the other property is once this connection goes away, once they both throw away the material on each side, it doesn't matter if you've logged what goes over it. You can't break into one of them and force them to reveal what was sent. Once the circuit gets closed, once they all stop talking about this particular connection, it doesn't matter if you've logged the traffic going back and forth. Okay, so she establishes a session key with R1, and from there she's going to write another packet encrypted with this green key saying, Dear R1, please extend this circuit to R2. And from there she's going to do the same key exchange and establish a yellow key with R2. So this means that R1 can't read the traffic going between R2 and Alice because it's encrypted with this key. And at this point, she's going to extend the circuit to R3 by writing a little message to R2, wrapping it up in both of these keys, the yellow one and the green one, and then sending it on. This guy will pull off one layer and say, well, this isn't for me, I can't read it, I'll send it on. And then R2 will pull off a layer and say, well, I don't know who Alice is, but whoever she is, she wants me to extend this circuit to R3. And at that point, Alice has done she's established a circuit. So she's got three different keys talking to these three different servers. At this point, she's going to hang out, wait, her Tor client will wait with a few of these circuits open, and eventually there will be an actual application request. She's going to click on CNN.com or something. And then her Tor client will say, oh, I have a request. I'm going to take a circuit that's available, maybe the one we just built, and I'm going to write a little request saying, please connect to CNN.com port 80. And I'm going to wrap that up in the blue key and the yellow key and the green key and send it down the circuit. And each one's going to pull off one layer until R3 reads it and says, I don't know who that is, but they want me to talk to CNN. I'll connect them. And at that point, Alice has basically a TCP stream being proxied all the way from Alice to Bob. And then they can just talk back and forth like normal. So once you've got one of these circuits, you can also connect to several different destinations at the same time over the same circuit. This is really important. For example, if you're going to AOL and they've got 71 tiny little pictures, you don't want to build 71 different circuits for each of those. Instead, you want to use the same circuit for 71 different TCP streams. So that's an example where it's good. You want to keep using the same circuit for a lot of different things. But it can also be bad to keep using the same circuit for a lot of different things. Because if you go to Amazon and you look about car racing, and you go to Wikipedia and you post about jump roping and astrophysics, all the stuff I was talking about a few slides ago, R3 doesn't know who you are, but they know whoever that is, they're doing all these different things. And it can start building a pseudonymous profile. I don't know who it is, but they're interested in this and this and this, and maybe pretty quickly it can start to recognize who that might be. So there's a trade-off there in terms of we really want to reuse the circuits so we don't have to spend time doing public key crypto, but we don't want to reuse them for too long. And there's an open research question about what the right trade-off is. Right now, we use the same circuit for 10 minutes before rotating to a new one. 10 minutes is probably way too long. But if we make it a lot shorter than that, then all the Tor servers spend all their time spending their CPU doing public key operations, and then they get angry and stop. So there are a lot of different sides to that trade-off. So far, so good? Great. Okay, so the Tor client is a SOCKS proxy. SOCKS is a very simple protocol. You just connect and you say, here's the address and port I want, and it says, okay, I'll connect you. So the main point of this slide, you can use SOCKS for web browsing, for IRC, for instant messaging, for SSH. But you need more than just communications anonymity or connection anonymity. There's also a separate notion of data anonymity, and that's where this little green box called Web Scrubber comes in. If you use your Internet Explorer directly with Tor, Tor will do its job. It will anonymize your IP address. Nobody will know what IP address you're coming from. But your Internet Explorer will send all sorts of exciting HTTP headers. It will say, I'm Internet Explorer version 4.7, patch level 3, build 27. And it'll say, I really prefer Japanese, but German and some other thing are fine alternatives. And it'll say, the exact number of pixels by the exact number of pixels of my window is this. And it'll say, here are all the cookies that I've ever seen from websites that look kind of like you. Oh, you've got Flash for me? I love running Flash. So all of these different application level things can be a danger for your anonymity also. Flash and Java and stuff like that are a particularly bad worry because they run arbitrary stuff on your local computer. So, for example, if Alice is willing to run Java applets, then she'll connect to the website, and the website sends back a Java applet that looks up her IP address and then sends it back over Tor. So Tor is doing its job. It's anonymously sending that IP address back. Nobody knows where it's coming from, but that might not be what Alice has in mind. So there are a lot of application level things that we need to worry about in terms of are we leaking information about our computer or our location or our network connection or something like that, separately from Tor's job. So there's a program called Provoxy that sort of tries to do a little bit of this. Firefox is getting a lot better at it. And we've got a new plugin, a new extension for Firefox called Tor Button that tries to tackle a lot of the application level stuff. I'll show you the interface later on if we've got time. But basically, in the bottom of your browser, it simply says Tor enabled in green. And you click it, and it says Tor disabled in red. And that's the whole interface. But behind the scenes, it's doing a lot of other smart things that try to keep you safe. Another point, we've got a control protocol that we added a few years ago. And that means that you can connect over a local socket that looks sort of like SMTP and say things like, please let me know if any important things happen, I'll display them to the user. Or please let me know what the current configuration is because I'd like to change it. Or please change the current configuration to this. And that means that people can write separate GUIs in Microsoft Visual C# or whatever the latest fad is, and they can be separate from Tor. Tor can still be written in C and be really portable, but you can have a controller for whatever platform you have in mind. And there's a nice fellow at RPI who's written a Tor controller called Fidelia that has slick graphics, and it graphs how much bandwidth you're using, and it's got a map of the world, and you can see your circuits being mapped and stuff like that. Okay, another point. Usability for server operators is key. Since our security comes from having so many servers around the world, we really need to make it easy for people to decide, I'd like to run a server now. So a couple of ways to do that. Rate limiting. We let you say, I want to provide only 40 kilobytes a second or only 200 kilobytes a second. I don't want to produce whole network connection for this. And then another half of that is there are a lot of people with ISP colo accounts where they get 60 gigabytes per month. So we have it set up so you can say, use 55 gigabytes per month and then go to sleep until next month and then do it again. So there are a lot of different features that we've added to account for various bandwidth accounting mechanisms. So another piece is exit policies. Every Tor server